Good morning. I'm Professor Richard Magin, former head of the Department of Bioengineering here at UIC. And we're here today to share reminiscences and remembrances of the establishment of the department, which this year is almost 50 years old. And one of the founding faculty members of the department is Dr. Bert Zuber. And Bert came here with Larry Stark, who was the founding department head, and we will talk today about his history with the department, his interests in bioengineering, and begin with these talks, what we hope will become a series of interviews with faculty and with colleagues of these faculty who have gone from UIC to countries and institutions all over the world. So this is an archival project where we're beginning to get in touch with our roots, trying to establish the field of bioengineering as it grew here and as it's grown in the country and worldwide. So with that as a preview and as an introduction, I'd like to ask Bert about his first experiences here in Chicago at UIC.
Well, first of all, I want to thank you for taking on this responsibility. It's very, very important. And we know you're a great debt for doing that. I arrived here in Chicago from Boston in June of 1965. I drove with my then wife and my two young sons, who were 4 and 1. So you can imagine how old they are now. And we took up residence in Chicago. And I actually had a summer contract, so started working right away. And at that time, we had a facility at Presbyterian St. Luke's Hospital, a Department of Biomedical Engineering, and a bioengineering program here at what was then University of Illinois Chicago Circle. And our offices here were in University Hall, believe it or not. There was no behavioral sciences building. It was a parking lot. And parking was free, if you can believe that. Our primary research facility was at the hospital. And we all set up labs there and began doing research in earnest. The line bioengineering faculty members, the real founding members of the department, were Larry Stark, me, Arnie Trollstra, Earl Goes, and that's, how many is that? 4? Mm-hmm. 4. Those were the people who actually had contracts in bioengineering. And there were other people in other departments who were associated with the effort, and also had labs at Presbyterian St. Luke's.
Was it an undergraduate and graduate program at that time?
It was strictly undergraduate. There was no approval by the Board of Higher Education to offer graduate degrees at that program. So our graduate degrees were offered through the Department of Physiology at the Medical Center.
Interesting.
Yes, very interesting. So that's the way it started. The campus here there was a lot of mud. And there were relatively few buildings. I don't think the library was open or maybe even hadn't been constructed yet. It was quite a scene. So that's the early history. Maybe you want to take it from here. Right?
Yeah. Well, what drew you into bioengineering? What aspects?
I did my undergraduate work at the University of Pennsylvania in chemical engineering. I had always been interested in chemistry, very interested in chemistry. And I found chemical engineering to be one of the most boring subjects that you can ever imagine. And so late in my undergraduate career, I became interested in biology. And I actually worked with a professor at Penn in biochemical engineering.
Who was
fermentation
that?
technology. Art Humphrey. And then I went to MIT for graduate work and did a master's degree in biochemical engineering. But then I realized that what I was really interested in was human physiology. So I sought out Larry, and that's how.
And so Larry Stark at that time was at MIT.
He was at MIT. He was a research associate at MIT.
Okay.
So he was completely free of academic responsibility and could devote himself entirely to
Right.
research.
But he was, as I understand, an MD, PhD.
He had no PhD. He was an MD.
Oh, I didn't know that.
Yeah.
Yeah. That's very interesting. I once tried to make a comparison and with early discoveries in biomedical engineering as being precipitated by either physicians or by engineers. And my bias, of course, was that engineers saw problems and tried to solve them, and physicians enabled that. But it turned out in example after example that I could concretely identify pacemakers and prosthetics and dialysis pumps. It was always the physician that came up with the problem and surprisingly tried to solve it.
Yes.
And I know in Larry's case, he took courses in control theory and learned about analog computers, and then took these concepts in partnership with his neurological training, and then tried to build models and measurements that he could view the brain. I've looked over some of his papers, and it was surprising to me how he wanted to deal with the complexities of Parkinson's disease or motor impairment, things that are challenges today, but he realized that he didn't have the tools. So he looked for a way into the brain that would give you insight, but also observation, and of course that's the eye.
Sure,
and the control of the pupil, control of the saccades that the eye, and other eye movements became an R, classic neural engineering models and neurophysiological models. Is that what you originally got interested in, or?
Well, actually, it's kind of brings back interesting memories. When I first went to his lab, I was looking for a PhD topic, and I had a background in chemical engineering. I knew heat transfer and fluid mechanics and all that sort of thing. So it occurred to me that a logical thing for me to do would be thermoregulation, control of body temperature. And I told him that, and I was a young.
I studied the thyroid hormone and its regulation in graduate school as a biophysics student. So I know where you're coming from. Yeah.
So and maybe you'll have a similar experience that I'm going to describe. I said to him, I would really like to do thermoregulation. Well, he was in neurological control systems.
Sure.
And it was so interesting the way he humored me for a while. And I remember. In order to do thermoregulation, you have to have a calorimeter and make very precise measurements of temperature and heat transfer and so forth. And so he sent me to Yale because they had a lab there that was doing thermoregulation.
So he actually encouraged you to follow your right.
I drove to New Haven with a fellow graduate student. Anyway, and we visited this lab, and I came back all enthusiastic. And in the end, it came down to what it always comes down to. It came down to money. He didn't have any money to support a project in thermoregulation, so I worked on eye movements.
Interesting.
And it was fine. It worked out just fine for me. I made a career of it. So, anyway.
When you came to Chicago, who were your first students here?
A couple of the first undergraduate graduates in 1969, I believe, 68 or 69, were Les Laskowski and John Allen and Stuart Abrams. Okay? And I subsequently became the acting department head.
In 70, 71, I think?
71, I think it was. And I hired them. We were short of faculty. We needed people to teach. I hired Laskowski and Abrams to teach courses. They had their master's degrees at that point. And so they were around for a while. But they were the first undergraduates.
Was the PhD program established in bioengineering soon after that?
I don't remember when the PhD program was established.
Because I think that probably required Board of Trustees and
Oh,
Illinois
yeah,
Board of Higher Education approval. And,
Illinois Board of Higher
right.
Education was the stumbling.
Right, and at that time I think the campus in Urbana probably had the only competing engineering program, at least in bioengineering, although it wasn't a department as I remember.
Yeah, they were.
It was part of electrical or mechanical
It
engineering.
was mechanical, I think, yeah. They did primarily heat transfer, I think, didn't they?
In mechanical, John Chato,
Yeah.
yep. And then there were a number of ultrasound people, I think, in electrical engineering. Well, thank you, Bert. You've told us about the beginnings of the department and your role in that. Can you tell us a little about how the department and the field of bioengineering changed with time, evolved here, and how your work perhaps changed?
Well, one of the things that happened was that our locus of activity was, as I said, originally at Presbyterian St. Luke's Hospital. We came to this campus to park and to teach, but we were on committees, but our real center of activity was at Presbyterian St. Luke's.
Because this is long before UIC was formulated by mixing the medical school campus with the Circle campus, and Rush St. Luke's Presbyterian is a separate institution then and now.
Yes, and it was one of the few examples of pretty good cooperation between the two institutions. I don't know that it's been matched since then, but you know more about that than I do. But eventually, and I think this sort of coincided with Larry's leaving in '68, we all realized that our paychecks were coming from here, and that this is where our primary role should be. And so we moved our activities primarily here. We maintained some presence at Presbyterian.
So the SEL behind us here was built, and when I first came here in the late 1990s, I noticed walking through SEL the listing of all the laboratories and under the name Department of Bioengineering on this floor and this floor and this floor, and it was quite extensive.
Yeah, and it expanded over time. But I had a lab in 4063 SEL.
Right, and we still today have some labs and instructional facilities up on that floor.
Yeah, and I think what's happened to bioengineering is that it's just simply blossomed and exploded. I mean, there's hardly a major university that does not have some kind of bioengineering program. They vary a lot in name. Like the one at MIT has a very peculiar name.
Biological engineering or something like that. Or University of Chicago has one now. I think it's molecular engineering.
Yeah. Well, anyway, that's pretty much what's happened. It's become a more legitimate field. Although there's still some people who, at least when I was still active, there were still some people who questioned that.
Yeah, I came into the field from biophysics, and I was in Urbana initially, and it was viewed as a hyphenated discipline. It was biomechanical, it was biochemical, it was bioelectrical, and people studied problems, I think as you and Larry started, with an engineering model, an engineering measurement system, but a medical perspective. And what I've seen over time is, if anything, the bio has increased from just BIO to bioengineering, and the discipline has become more fundamentally connected at the molecular and cellular level with biology.
Well, that all happened after my time. But it's interesting that you describe it that way. I always, early on, as a graduate student, was determined to get as much biological knowledge and training as I possibly could. And it was because one of the principles that I sort of lived by was that there was a difference between somebody who was trained as a bioengineer and an engineer who worked on biological problems. And I was given the responsibility of constructing the undergraduate program in the department.
Mm-hmm.
And when I did that, I made sure to include enough biology and physiology so that our students would graduate with sufficient knowledge to be real bioengineers. So that was always a guiding principle to me, and I was glad to have that opportunity to influence the original.
Well, I think I call them the 3 Ps, the pumps, the pacemakers, and the prosthetics, are really the foundation of biomedical engineering.
Uh-huh.
And with the biomedical focus, it's natural that physiology, biology, pharmacology, these disciplines be blended together with an engineering model and mindset.
Yeah.
When I first came here in '99, my first students graduate students here were required to take the physiology courses in the College of Medicine. That's probably some of your doing.
Your graduate students?
My graduate students,
Uh-huh.
yeah, the full year of physiology. And to this day, one of my students insists, on one hand, it was the hardest thing he ever had to do. On the other hand, it was the most useful thing that he did while a graduate student, because now as a professional bioengineer, he can seamlessly move into almost any medical problem or discipline with the ability to communicate and understand without having to, quickly thumb through some books.
Yeah.
So the field certainly has expanded, and I think the perspective has changed.
Yeah.
I think just as biology became very more molecular, DNA oriented, and sort of the systematic analysis of heart, lung, kidney that was the first interest, I think, of the bioengineer, don't hold the pride of place that maybe they held 100 years ago.
Yeah, absolutely.
So in looking at these areas, I noticed that your background started off in the liberal arts. And I wondered if that's not usually the path into engineering. And I wondered if that perspective has carried over somehow into your interests or professional activities.
Well, this actually relates to something that I mentioned earlier, namely how boring I found chemical engineering was, because my background started in chemical engineering.
Right.
When I went to Penn, I was a chemie major.
Oh, you started in chemie, okay.
Yeah, and as I...
You got so bored that you took some LAS courses?
I actually got a BA.
Oh, okay.
I did
that's more than being bored.
One of the
Okay.
earliest 3-2 programs. I had to design it myself.
Yeah.
I got a liberal arts degree mainly to preserve my sanity.
So
I loved it.
Right. So you were interdisciplinary in the general sense.
I thought about that.
Yeah. Were there books or professors or conferences that sort of cemented your interest in moving into bioengineering as opposed to going into some other field?
I think what originally got me really interested in science was high school teachers. I had a high school physics teacher, a high school chemistry teacher who were just outstanding. And they really cemented that interest for me. And my interest in chemical engineering was because, as I said earlier, I was very interested in chemistry, and the older brother of a childhood friend of mine was a chemical engineer. Okay. So I had an opportunity to interact with him. He worked at a sugar refinery in Sugar Land, Texas.
Okay.
And he used to bring me test tubes and flasks and beakers and stuff. So anyway, Houston was a big oil town, and petroleum engineering was really big. And so it just sort of seemed a natural thing for me to do.
Yeah, well, Schlumberger offered me my first job.
Oh, really? You didn't take it?
No, but with a bachelor's in physics, you have to look for what you can get. And analysis of oil and gas and making measurements was what I was interested in doing.
Huh.
But I think the biological sciences weren't really the first thing I thought of. I think chemistry also was something that was the first hands-on activity that was quantitative, that I was able to see. There was a recent book you might have read called Uncle Tungsten by Oliver Sacks, the noted writer and neurologist, Uncle Tungsten. And it's the same thing as your situation. He had an uncle who worked in a factory in London that made light bulbs. And they used tungsten in the filament. And as a young boy, he set upon as a goal to try to isolate or identify every element. And that was back in the days when you could, with an uncle or with a helpful pharmacist, get your hands on mercury and sodium and most every other element in some simple form that it could then be crystallized or explosive. But I believe that engineers are maybe made, not born, in the sense that early in one's career you need opportunity, you need inspiration as you had, you need the proper respect for education, but it's also important, I think, to have your hands on something. And I worry myself about today's generation because the things in their hands they can't take apart easily the way we could take apart a phone or a radio.
You'd be surprised.
And I really believe in young people that if you don't take things apart, if you don't manipulate things when you're young, the brain doesn't get properly wired. There's talk about the connectivity of the adolescent and the pre-adolescent brain being greater than the adult, and that there's a process of pruning that goes on with maturity. And that pruning when you're handling and manipulating things and visualizing things, I think is important. And also it just establishes when you build a rocket or a bomb, back when it was fun to blow things up, it gives you a sense of accomplishment and a little bit of risk, and then you can move forward with that.
Interesting.
So do you have any advice or words of wisdom for students in bioengineering starting out today? If you had it, if we could do it all over again, what have you learned that you think could be helpful? Or
well, I think the only advice that I would give them is just to be calm and don't panic, because I think that young people have a tendency to do that. And I think my own history sort of reinforces the notion that it doesn't matter so much the details of what you do as long as you sort of follow your interests, and it'll be okay.
Okay, that's reassuring.
I have two granddaughters in college, one of whom is graduating actually, and that's pretty much what I've told them. It doesn't matter so much where you go, if you're
happy and confident in what you're doing
and curious, it'll be fine.
Good. Is there any other observation that you'd want to share with us about the early colleagues or interactions here or elsewhere?
Well, of course, it was very exciting.
Present at the creation, so to speak.
Building things from sort of the ground up. And as you probably well know, it's been a very stormy history. In 1992, which was 2 years before I retired, the department was dissolved.
Wow.
And my bachelor's degree in chemical engineering came back to haunt me because they had to distribute people, and I ended up in chemical engineering. So then the department was reformed in
98, I think, or
was it that late?
Maybe.
When did
I came in 98.
Okay.
My understanding, in 92, I was in Urbana. And I remember we were blamed as being behind the plot.
There was plenty of blame.
They tried to spread it around, and they thought maybe we had aspirations for a department down there, and we did. And since we weren't making any progress, we had to first do away with the one up here. And as far as I know,
I don't believe that.
I was never
there was plenty of it. Well, I don't
privy to any information about that, but. I knew Jim Lynn, who was the department head, quite well, because he and I had done some graduate work in the same fields. We didn't work in the same labs, but we worked in the same area. And I'd been here visiting, giving seminars and such. But I was somewhat surprised that the department was dissolved, but it wasn't my problem to deal with. Later on, when the department was reformulated, and as you say, it was really bad timing, because in the late 90s, the Whitaker Foundation came on the scene with a lot of funds targeted at institutions that would create bioengineering departments. And so it was a time of growth and development of the discipline, and the fact that UIC was going south when everyone else was going north was unfortunate.
Absolutely. Yeah.
And so I had also had difficulty in Urbana trying to build the program there into a department, following in your footsteps and in Larry Stark's footsteps. The dean there didn't see the rationale, and from his perspective, looking back, I can see it. I mean, there's no major hospital, there's no major biomedical research enterprise going on here. Maybe we should just concentrate on lasers and computers and things that we can manipulate ourselves. And bioengineering, in addition, is very expensive. And what we have today, where in some ways, we've gone back to the way it started in our close linkage with the College of Medicine. The department today reports to both deans in medicine and engineering. But when I came, there was still a feeling that bioengineering needed to be reorganized. And in some ways, it was good that, maybe we should, don't tell the dean this, but maybe we should do this every 5 or 10 years, dissolve a department, distribute the faculty, and then reassemble in a new mixture, just sort of like reshuffling the deck. It gave me an opportunity to move away from these hyphenated disciplines and move bioengineering back toward the emerging fields of tissue engineering, bioinformatics, neural engineering. Because for the first time, we had the tools, I think, that Larry and you did not have to interact with the brain, interact with the neural systems in such a way that we possibly could make some real advances in terms of both actuators and functional measurements. And so I thought this was I took this as an opportunity. I had been frustrated in developing a department in Urbana, so I figured, I didn't figure. The dean at that time figured. He said, "Why don't you put your money where your mouth is?"
And who was it?
That was Kennedy.
Okay.
And Larry Kennedy, and it was funny because he approached me about the job, and I said I'm not interested. And they interviewed a bunch of people, and things didn't work out. So he called me again and said, "Well," I said, "Oh, okay. Well, I'll come give a seminar." And then I came, I think, with the same feeling you came, that this is an opportunity to build something and to put a stamp on something. And as Larry came, probably with you and others as the first department, I came and hired the first 3 department members in bioinformatics, neural engineering, tissue. And we had 4 again. It was 1999.
Yeah, but that's key. You hired the first 3 department faculty from our inception in 1965, probably until you came in 98, 99, yeah. The bioengineering program department, whatever you want to call it, had 4 budget lines, period, or 5.
Wow.
And there were a series of assistant professors, untenured assistant professors, that rotated through that 5th budget line, and not one of them got promoted. And you probably want to edit this out of the tape. But it was shameful. It was really shameful.
Well, and this is, I think, part and parcel with this hyphenated discipline, because if you have to report to 2 masters, you have to have engineering and medicine, or biology and engineering as your disciplines that you're going to achieve tenure in. And now the department is split in such a way that we can have new faculty
Sorry, I'm going to have to beg to differ with you about that, because these young guys were were straightforward, non-tenure track faculty. They did everything they were supposed to do.
Oh my gosh.
And,
Oh, this is sad.
And we would send them up for promotion, and they'd get bumped upstairs. So
that's sad.
We probably should not go there.
Okay. Well, I'm happy that you came here. I'm happy that we're here and able to talk about these things, and I'm very pleased that we are putting together this series, which I think will share our observations and perspectives with others, whether they want to hear them all. Mm-hmm. And with that foundation, I think. Make sure that there's a solid base of understanding of what the department was 50 years ago, what it's gone through and what it's still going through, and how this process has led to what we are today, and what's the story about, you can't plan the future without knowing the history.
Good.
And I think by knowing more about our history, we can be a little wiser in the way we deal with current and future problems.
Well, I think you and I share that philosophy.
Okay.
And the one thing that I didn't say, in 1998-99, things really started when you came here, and you were really responsible.
Well, thank you. Yeah.
For the blossoming of the department and into what it is today. It's just amazing.
Yeah. Well, in looking back through the history here, I've been amazed at how thoroughly you guys had plowed the field and planted the seeds. Because when I look back, there's a current book out, The Innovators, by Walter Isaacson, talking about the development of computers and the internet. I mean, the computers at Penn that were, I think, Eckley, I think, and had set up some of the first digital computers. And what was startling was the contributions of McCullough and Pitts, who were here. The contributions of Stark and yourself to the early neural engineering. I mean, we look at the Rehab Institute of Chicago, we look at the neurological institutes here on campus, and all of this grew out of the work that was pioneered back then. Yeah. And so you can't just build something from nothing. There has to be a fertile soil, and there has to be a structure and an environment that we succeed in. And in looking back in organizing this series of talks with you and with others, I'm amazed how many faculty are still here. Joel Michaels, you were just pointing out, was a graduate student contemporary of yours. Bill O'Neill, I think, was one of the faculty members, followed right on your footsteps.
Well, he and I came at the same time.
Yeah, so I mean, we still have these present at the creation individuals. And I'm looking forward to more conversations and more dialogue to get the complete picture. Okay, it's required in interviews like this to ask experienced, knowledgeable experts to project that experience and knowledge into the future. I'm not sure that any of us who fall into that category have a very good record of success, and we won't be around to see our failure. But it's appropriate to try to project along the curve of development that we've talked about here this morning, of the department, the discipline, and the interactions with people. I look back to the field of cybernetics and the development of neural engineering, as we would call it today, out of neurology, out of electrical engineering, out of a real blending of quantitative measurements and models with, unsolvable, not well understood neurological problems. And pioneers in this field, to my knowledge, goes back to many of the individuals who were at MIT when you were a graduate student. I think McCullough was there. Certainly Larry Stark was there. Levine, I think, was it Levine?
Levin.
Jerry Letvin. Yeah. And he had I think I think it was Norbert Wiener. He was in New York, though, I think.
Yeah.
Right. And this cybernetic idea of I think he coined the definition in terms of communication and control between man and machines, which is still pretty apt.
Yeah.
And I think our interest in networks, our interest in neural control, our interest in fixing misregulated systems points from then to today. So I think I think it was Steve Jobs was saying that everyone wants you to connect the dots. Well, but you can only connect the dots looking backwards. You can't connect when the dots aren't out there yet.
That's right.
And so we can't, if I threw the dots out, you could draw a curve through them and say, well, of course, this is why we're sloping upward, or why we're not going quite as fast as we thought. But when you worked here with physicians at Rush St. Luke's Presbyterian and at UIC, were there instances or individuals that are dots that you could now connect to project forward?
And that's an interesting question. When we came here in '65 and had this major connection to Presbyterian St. Luke's Hospital, there was a real effort to interface with the medical community. And as a matter of fact, I was the head of the Biomedical Engineering Consulting Service at Presbyterian St. Luke's Hospital.
I saw on your title that you were an attending biomedical engineer.
I was actually on the attending staff at Presbyterian St. Luke's Hospital.
Even today, with our great interdisciplinary relationships with the college, I've never heard of a bioengineering professor called attending anything.
Very jealously guarded by the physicians, and I don't know how they managed to give that up. But yeah, we all had it attending.
That's a fairly high level of status within the medical hierarchy.
It is indeed, yeah. And anyway, so the Biomedical Engineering Consulting Service was an entity that was supposed to give physicians engineering help with solving medical problems. And so the people on the medical staff were supposed to come to me with their problems, and I was supposed to help them solve them. And there was a lot of interaction, and people came with sort of very interesting problems. And so that was a very interesting aspect of that whole operation. I remember working with surgeons, as you were mentioning earlier, how innovative surgeons are in terms of designing things and building things.
Again, it's part of this hands-on training, I think, as a young person.
I remember a young surgeon, Dave Roseman, who was very tight with our department and brought us any number of problems to solve. And I sort of kept up with him over the years and actually ran into him in a drugstore maybe 10, 15 years ago, and was surprised to see how much he had aged. Because he was a young, starting out attending. So that was very interesting.
So in the future, clearly where we appear to be going is a more blended profession. It's now blended in the curriculum, as you started with. We have bioengineering courses every semester, not just junior, senior year. We have.
Okay.
I mean, as freshmen, sophomore students, they're learning about the problems. They don't have all the tools to solve them, but it's not a structured, layered thing where you have to first learn all the math, physics, biology, and chemistry, and then we'll talk about how the heart works.
That's an engineering, it's an engineering thing, isn't it?
Yep.
That's why so many kids are bored to death with engineering the first 2 years.
Right.
So, do you still have BioE 200? Introduction to bioengineering?
It's 100 now.
Is it 100? Well, that was a course that we taught, I think, at the sophomore level.
Right.
So,
right. Yeah. Well, there were a lot of disciplines where the sophomore year is the decide year for committing to a major.
Right.
But bioengineering is blessed with really strong students that know what they want to do. Approximately, we have students coming in who are, some of them are keen to go into aspects of the medical profession and they want to do it with a technological base.
Sure.
And others want to get to graduate school as soon as possible.
Yeah.
And others want to go to work and apply these ideas in new and novel ways. So I think that the blending is working. I worry sometimes that the pendulum, which always seems to occur in most disciplinary and academic venues, swings back and forth between biology, engineering, medicine.
Yeah.
And so we have to make sure we don't throw out some of the essential tools that the students and the researchers in the future will need.
Mm-hmm.
So is there any other aspects of your history here?
It's interesting to think about where the field is going. When I was a graduate student, I was determined, as I said earlier, to get as much biological knowledge as I possibly could. And I took the graduate level biochemistry course at MIT, which was
an adventure.
A dog. I'm telling you, it was a bear.
Yeah.
It was one of the hardest courses I have ever taken in my entire life, and I won't tell you what my grade was. But I was taught biochemistry by Vernon Ingram, who was into the molecular biology thing in 1965, 66. That's when all the DNA, RNA stuff was happening, and it was happening down the street at Harvard.
Right.
So it was a fascinating experience to take that biochemistry course. And it never occurred to me that what would happen in bioengineering is that it would become molecular. It would become cellular, because it wasn't at the time. It was systems. It was physiological systems. And so that's been one of the things that has sort of surprised me, but in retrospect, you can understand.
See where it's going, right? Yeah. Just like molecular biology, and right. And of course, having the biochemical knowledge, you understood the importance of proteins and lipids and carbohydrates, and not only the DNA, but the whole metabolic structure and
metabolic pathways.
Yep. Yeah. No, I was, when I took biochemistry, I had the same experience. It was dreadfully difficult, and it opened my eyes to. There were some networks and diagrams and circles and feedback, and I was amazed that they didn't have differential equations next to these things. I mean, they just, you had to remember the names and connect them.
But it all made sense.
I remember I was perplexed on a exam one time in biochemistry, and I had this sugar and I had that sugar I had to get to, and I'd forgotten the pathway. So this had a methyl and this had a hydroxide, so I invented an enzyme, a demethylation hydroxylate. And I wrote it in and made it, and I got back a nice little note from the professor checking it correctly, saying, "How did you know about that enzyme?" Because it was something that was, I just pulled it out of the air. And I think, unfortunately, or fortunately with nature, a lot of things like that, if it's possible, it's probably essential.
Yeah, absolutely.
And so I think the big problem with bioengineering I see is that it's a 5-year curriculum forced into a 4-year.
It's always been a struggle.
Yeah, and I think to get the depth and breadth is always going to be
you have
the
to
difficulty.
Be very careful.
Yeah, but I think we're fortunate in that we get investigators like yourself, we get leaders like Larry Stark and others in this department, and others that want to move us forward into the future.
Yeah.
And I think these leaders are important because of what you were saying about your teachers, and it's the folks that you see when you're developing your ideas that become your role models. And then sooner or later you have the gray hair and you're sitting in the chair and people are asking you to reminisce and remember what it was that got you there.
Yeah, it's interesting to speculate about where things are going. Just as I didn't see that things were going to go molecular and cellular when I was a graduate student studying that stuff, where is it going to go?
Well, in the past we thought it was going to go into space. I mean, aerospace medicine, developing systems for monitoring in weightless environments, rockets to the moon. I fully assumed we would have bases on Mars today.
Okay.
And there's still talk today about maybe a moon of Jupiter or something like that.
Right.
So it could be in the future, as we try to deal with limited resources on this planet, that we have to think again about how to be more efficient and self-sufficient, and to do that.
Well, I'm sure you've done your share of grant proposal refereeing. and scientific paper refereeing. And you always used to see somebody justifying their bioengineering research with a proposal that this has clinical implications. This is going to lead to a cure for Parkinson's disease or whatever. And I'm not sure that that dream has been realized significantly. So it just reinforces the notion that
well, I think
we don't know where it's
well,
going.
I think with the I would agree with you at the molecular and the disease mechanism level. At the device level, we have spectacular neural implanted pacemaker, dialysis, insulin pump systems, and I think things that we're engineers, things that can be fully quantified and modeled in a deterministic way, we can build.
Okay.
It's the complexity of some of these biological neural pathways and genetic networks that make it so difficult.
Yeah, absolutely.
And it's presumptuous to think that you can go forward and solve that. But I'm encouraged when I look back at some of your some of the books and conference publications that you've donated to our archive. When I look at those, I see the same circuits that I teach today, maybe with some more fancy MATLAB computer methods, but the basic insight of identifying a structure and a function and building in the feedback and trying to predict what would happen if there's an imbalance or a change in the system, it's part of what we try to do.
Yeah.
And it has to be a partnership, I think, with biologists and physicians. And I think we just have to keep up the work and the effort and try to move forward and not oversell it. It's difficult in any kind of grant or publication mode to do this without just falling in line behind what everybody else does.
Right.
But those of us who are fascinated by biomedical, bioengineering problems, I think are going to have work to do for a long, long time. It's in a way, I'm old enough now to where I have family and friends who have passed on, and it's conversations like this. I think, gosh, I'd like to talk to Bill about this or Tom about that, because I know they would have gotten a thrill out of seeing that this could be done, and we talked about that at one time. And hopefully with these archives we'll be able to provide this snapshot and this window of some of those folks and remember and share with a future generation what we're doing. So I think in closing, I'd like to thank you once again for coming here today and for sharing with us your insights and knowledge. We have a little reference here. We have something we want to give.
I would like to thank you for your efforts in getting this going and keeping it going.
Well, we'll hopefully do this more frequently and make it a part of our living history. I've always seen that, but it's good to see it now in action. So I'd like to thank you, Bert, for coming, and we're going to allow you to be appropriately garbed when you leave here, and nobody can do anything without a T-shirt and a coffee cup. And so now you can wear your T-shirt as a UIC bioengineer.
Thank you.
And drink your coffee or tea, and
I really enjoy this.
watch this video and the others that we'll make in this series. So
Great. Thanks
thank
a
you.
lot.
Appreciate it.
Cut.